All right, so what we want to look at here is how do we distribute solar energy from one place to the Earth, from one place on the Earth to another. All right, so first off, how is energy distributed on Earth? Well, more of it hits where? The most energy is received at the equator. Okay, again, that's that latitude thing we talked about, one of those factors that affects climate. Okay, more energy is received at the equator, so there's more heat there, and it has to move, because of the second law of thermodynamics, from the equator towards the poles, okay, in order to balance, okay, that energy. That's what it's trying to do. Okay, but it's not just energy that causes our atmosphere to move. Sometimes there's differences in pressure from one place to another. All right, so differences in pressure will cause changes in the path of that air. All right, if there was nothing else, just the changes in energy, air would always move from north to south, okay, or south to north. It would just always circle in one circle. But there's more to it than that. There's differences in pressure, okay. There's strange surface features that can alter the path of air on the Earth's surface. There's all of those kinds of things. Okay, everyone follow me on that? All right, so that's what we're going to look at. Okay, we're going to look at the role winds play in distributing energy. Well, winds, we already said, is basically just evidence that convection is going on. Okay. We're going to look at the Coriolis effect. That's a big one. Okay, the Coriolis effect is the reason why winds don't always come from just the north or just the south. Okay, for us, our prevailing winds typically come from where? From the west or southwest. Okay, typically, they don't always. Okay, we know that when the winds come from a direction other than that, that we're in for something. Okay, that there's going to be a change in the weather, often severe. Okay, but we'll talk about why that is in a minute. Okay, and recognize that global wind patterns are a product of convection and the Earth's rotation. Okay, those two things work in concert with each other, because the Earth's atmosphere is not chained to the Earth's surface. So they don't move together. The Earth actually rotates under the atmosphere to some extent. Okay? So if I'm standing on the Earth's surface and the Earth's atmosphere is stationary, I'm moving through it. Does it feel windy? Okay? You stick your head out the window of a moving, not that you would ever do that. Stick your head out the window of a moving car. Does it feel windy? Does that mean it actually is windy? No, but you're moving through the air at a high rate of speed, so to you it feels that way. Okay? Well, to some extent, that's also what goes on Earth. We're moving through the Earth's atmosphere as a result of standing on the Earth's surface, which is spinning. Okay? And that leads us to think air is moving one direction when it may actually be moving in another. Okay? All right, so the Earth's atmosphere is in perpetual motion, and that's trying to eradicate differences in pressure and, more importantly, differences in energy. Okay, the amount of heat at the equator versus the amount of heat at the poles is the main thing driving the movement of air. Okay, but those changes in pressure can also cause that to some extent. So the Earth rotates this direction. You can see that gray arrow on the Earth here, kind of, I'll drop a green one on there. Okay, the Earth rotates in that direction, which is why this morning at like 4:30 when the sun rose, okay, we would have been kind of over here. Right? And as a result, standing there, we look to the east and we see the sun coming up because we're rotating into the sunlight. Everyone follow? Because obviously the sun isn't moving around. Okay, we're rotating underneath it. All right? Now, at this point in the day, we're probably, well, maybe not there, but maybe a little bit further back, something like that. Okay, we're in that position. The sun is starting to be not directly overhead, but kind of off to the west. And as the day goes on, okay, we'll get over to this point and be looking over to the west and seeing the sun go behind the mountains. Okay, everyone follow me on that? If we're doing that, it's going to appear as though the air is moving because we're moving through it. All right? Now, there's more things going on than that, but if the Earth's atmosphere was perfectly stationary, that's what it would feel like. Okay? It would feel like us moving to one side through the air. Okay, so like we said, nature doesn't like imbalance or inequity, and variations in temperature create variations in pressure, and as a result, air moves from areas of high pressure to low to restore balance, and we detect that obviously as wind, okay, because of convection and the second law of thermodynamics. Okay, so important for us to know sort of the root cause of that. All right. So the first major mechanism by which energy is transferred on Earth is wind because of convection. The second major mechanism that transfers energy we talked about already in the last lesson, latent heat. Okay? The third major mechanism that moves energy around on Earth is the jet stream. Okay? And they're in this order. Okay? Number one is convection. Okay? Number two is latent heat. And number three is the jet stream. Okay? The jet stream is the monkey wrench that messes everything up. Okay? Were it not for the jet stream, everything would just go along happily. Wind would always come from the same direction, right? There wouldn't be any changes in weather. Weather would be the same all the time, okay? And life would be like super easy at that point because you'd always know what to expect. Now, that would actually be bad because then a lot of places would be ridiculously hot and dry, and other places would be ridiculously cold. Okay, some places would always be wet, and you would never get any change. The jet stream is what causes changes in the weather. All right. So what the jet stream is it's a very high altitude wind. All right, up to like it can be 1 to 3 miles thick, but it's very, very high. Okay, like we're talking almost always over 8,000 meters above sea level. Right? So basically, you would almost never be able to detect it unless you were standing on some of the world's tallest mountains. Okay? And actually, as a climber, you have to be mindful of the jet stream and its movement. You always check satellite stuff, and you have someone at base camp who's telling you what the jet stream is doing. Because if you're on the top of a mountain when it comes, you're dead. All right? Because it blows fast. Okay? We're talking well over 100 kilometers an hour. Okay? And it's bringing changing air masses to you, which usually means whiteout conditions, snow, all that kind of stuff. You don't want to be caught in the jet stream. Airplanes use it. That's why it's called the jet stream. Okay? If you're flying from west to east as a pilot, you try to get in the jet stream because it acts as a big tailwind. Right? You'll probably arrive ahead of time. You'll use a lot less fuel, which doesn't really benefit you or I as a passenger. We already paid the price of our ticket, but okay, they like it because they use less fuel. So yes, you can capture it that way. However, if you've ever been on a plane where there was a ton of turbulence, you are working against the jet stream. Okay? If you're flying from east to west, generally they have to know where it is and they try to avoid it. They know what altitude it's at, so they'll change altitude. You probably had that experience. If you've been on a plane, you start to get the bouncing up and down sensation. They usually say, oh, well, we're going to descend. We're going to turn the fasten seatbelt light on, and we're going to descend, or we're going to ascend, and we're trying to get out of this jet stream and out of this turbulence. That's what they're doing. Okay? It can be quite dangerous. Right? In fact, that's why now, if you've been on a plane, they say, the captain has turned off the fasten seatbelt sign. You are free to move about the cabin, but we would encourage you to stay in your seat with your seatbelt fastened. The reason for that is if you catch any turbulence or you suddenly rapidly enter the jet stream, okay, the plane can either be thrown radically upwards or it can be thrown radically downwards by the change in pressure of the air. Okay, this happened on a flight, a Japanese airline flight about 20 years ago. Nearly half of the passengers on the plane and almost the entire flight attendant crew were killed because they got their necks broken. Okay, they were sitting in seats, not restrained, not wearing their seat belts, and the plane hit one of these air pockets, and the plane just rapidly fell. Okay, and it was actually forced down by the air. Well, simple physics says, Newton's first law says that if you will continue to do what you were already doing, that inertia thing we talked about. You continue to do what you were already doing unless acted upon by an external unbalanced force. So if you're sitting in your chair, not restrained, you continue to move forwards at that level until acted upon by the external unbalanced force of the overhead bin. Okay, so the plane drops, you don't. The force acted on the plane, not you. Okay? It's the same thing when you get in a car accident. Okay? You're supposed to wear your seatbelt. That way you're attached to the car and you do what the car does, which is stop. If you're not wearing your seatbelt, the car stops and you don't. Okay? Well, it's the same thing on a plane. If the plane drops and you don't. And that's what happened to the passengers and a lot of the flight crew because they were standing, serving, meal or drinks or whatever. Okay? And when the plane dropped, they stayed where they were. It would have looked, if you were on the plane, like they jumped up in the air, but it didn't. The plane fell and they stayed put, and they hit their heads on the upper surfaces of the plane. And okay, it was so violent that a lot of their necks were broken. A lot of the other people had spinal injuries, okay, and things like that. So the jet stream is quite violent. Okay, it can be anyway if you're not prepared for it or ready for it. Okay, I had a flight when I came back from Houston. It was the worst flight I've ever been on. Okay, and it was just we had to cross the jet stream because it did this. We actually crossed it twice on the way back from Houston, and it was horrid. Okay, like you're bouncing up and down. My computer actually at one point was like 6 inches off the tray table, just right up in front of my face. Okay, just because the plane dropped, and of course my laptop was not attached to the tray table. Okay, there were a few people beside me whose drinks were in their lap after that. Okay, so you have to be kind of ready for those things. So what the jet stream does is the jet stream's location and path are influenced by air masses, especially high pressure air masses. So it can't go through them, so it's forced around them. But the movement of these air masses causes the jet stream to turn and assume weird shapes, okay, like this one. And so the jet stream goes around this high pressure area, but when it does, it forces the air in this area to come with it and start moving. So we get this chilly air being forced southward through the prairies here. Okay? So on this particular day, we would have had cooler temperatures and probably even some precipitation. Okay? Down here, the jet stream kind of goes out to the side and goes out over the ocean. What's it going to pick up over here? Yeah, warm, moist air. And it's going to bring it right back in here to meet up with all this cool air it started moving just before that. Okay? Well, the interaction of those two things creates unsettled conditions right through Tornado Alley. Okay? This is the kind of thing that in the summertime sets up those kinds of conditions. Okay? The movement of the jet stream. Now, the jet stream's not going to stay on this path for very long. So that unsettled air and that unsettled conditions might last for a couple of days. Okay? But as these high pressure areas start moving around, okay, the location of the jet stream will change and weather will change and go back to normal. Okay? But the role of the jet stream here is that it moves air masses to places they wouldn't normally go. Right? And as a result, it brings in precipitation and latent heat that might not have been there otherwise. Okay? If it wasn't for the jet stream, we'd be a lot drier here. The only reason we get precipitation is because moisture is brought in from other places. We don't have enough of it here to really feed our own kind of water cycle. It has to come in from other places. That sort of makes sense? So that's the importance of the jet stream, is that it's the product, basically, of these two things, but helps to make them not always the same, which is important. All right. Now, global wind patterns. We've already said our prevailing winds come from the southwest. And the reason for that is because we're up here on this part of the earth. Okay? And on that part of the earth, air is generally moving northward. Okay? Air near the surface, pardon me, is moving northward. And down here, closer to the equator, the air that's near the surface is moving southwards. Here's why. The equator gets the most solar energy. Okay? We've said that already. So air that gets warmed up moves upwards. Hot air rises. So as that hot air rises, cool air from further north moves in to replace it. So air near the equator is usually coming out of the north because the other air that's been warmed up is higher up and it's moving north as well. Or it's moving to the north. This stuff is moving from the north. All right? As that movement of air is going on from north to south, the earth is spinning underneath it. So instead of appearing to come straight out of the north like it should according to this, it feels like it's being deflected as we move through it. So it's not coming straight from the north, it's coming from the northeast. That's where the prevailing winds come from near the equator. In fact, they're so reliable that they're called the trade winds. Okay? They have a special name. Southeast trade winds, northeast trade winds. Okay? They got that name because back when when the only way to get to the New World was by boat, that was how you got here. You couldn't sail directly from, let's say, England to Newfoundland across that stretch of ocean by sailboat because the wind doesn't blow that way. So you would have to sail like down the coast of Europe until you got low enough that the winds were blowing from east to west. You catch them, you go across, and then you sail back up the coast of the Americas, and then you can catch the westerlies to take you home. Right? That's why they got the name the trade winds. They were part of the trade routes that ran basically from like Spain and Portugal, okay, over to the New World. Okay, that sort of making sense? Okay, so these prevailing winds are the product of convection. Hot air rises, cool air descends, so we get these currents, okay, and the movement of the Earth. Now, up where we are, generally the air is moving northwards. Okay, near the surface, moving northwards, and it's warm. So we get typically that air gets pushed up in our latitude. So as the air is trying to move north and the Earth rotates underneath it, it actually pushes it from west to east. Okay, so we typically get westerly winds or southwesterly winds. Okay, now we're kind of near the top end of this, which is why weather in Alberta is rather unpredictable. Okay, I mean, we have a saying in Alberta: if you don't like the weather, wait 5 minutes. Okay, because weather in Alberta changes all the time, and that's because we're right here on the border of the westerlies and the polar easterlies. We know when the weather changes, the wind's going to come from the north or the northeast, and it's going to bring nastiness with it. All right, we know that when the wind changes, that's what's going to happen. Okay, so that's kind of why we're right here on the edge, okay, of that border. Okay, so being able to explain how this works is pretty important. Okay, so we've got this rotation of the air due to convection and the rotation of the Earth causing that deflection. Everyone's good with that? Okay, this rotation of the Earth deflection is called the Coriolis effect, okay, which we'll get to in just a minute. Now, it's hard to see this on Earth because our atmosphere is transparent. So we can't see the movement of air unless there's a lot of cloud. Okay, and then sometimes you can follow the path of the clouds. And if you can actually see that always above 30 degrees north latitude, the clouds are moving to the east. Okay, and at this latitude, the clouds are always moving to the west. Okay, but again, unless there's clouds present, you can't really see it. But you can see it really well on planets that have opaque atmospheres. Okay, I'm going to show you a video here that's of a couple of videos of Jupiter's atmosphere. And it actually looks like part of Jupiter spins one way and part of it spins the other way. Right? Because Jupiter is so big, it has more bands than we do. We have 3 bands per hemisphere. Okay? Jupiter has like 5 or 6 because it's so much larger. Okay? And so what you can see is that here at the equator, okay, Jupiter's moving this way. It orbits, or sorry, rotates the same way we do. Okay? But its winds at the equator are doing this. This band is doing this. This band's doing this. This band's doing that. Okay? And then, you know, kind of all the way up. It's really odd, okay, that it does that, but that's what goes on. Okay, so I'll show you a video. You have to ignore the really cheesy computer voice that says all these stupid things throughout the whole video. It just has a good video clip of the movement of air, so I'll show you that. Okay. All right. Okay, now the Coriolis effect. This is kind of the big thing because I always have a question about, you know, explain how the Coriolis effect and convection can contribute to prevailing winds, and that's kind of one of the things we've got to remember. So the Coriolis effect is this deflection. Okay, the deflection of those winds that are trying to move north-south but can't because the Earth is spinning underneath them. They still move generally north and south, but they get deflected either east or west depending on where you are. Okay, so we've got this rotating Earth, okay, and it's moving underneath. So if I was to, let's say, roll a ball from the top of the Earth to the equator, okay, I wouldn't hit the spot that was directly below the ball when I released it. I would hit a spot further over. I would hit this spot, okay, because my target would be gone. The ball would roll straight down, but the target would move while it was rolling, and as a result, I would miss it. Okay, so I'll show you here. Okay, so I've got this soccer ball that's going to represent the Earth. Okay, and I'm going to draw a line down its face. Okay, and I'm going to move the marker straight down. Okay, from the North Pole to the equator here, and I'm going to spin it this way as I go. All right, now there's some seams on there that'll probably catch my marker, but hopefully it'll still work pretty well. Okay, so I'm moving the marker straight down, but I'm spinning the ball as I go. What happened to the path of the marker? It's curved, right? Sort of. It's curved a little bit. Okay, right? So it's curved because as I move the marker straight down, I move the ball. Okay, so can't draw a straight line if the ball is moving underneath the marker. Okay, and a similar thing happens at our latitude. Okay, the wind's trying to move upwards, and the ball is moving with it. Okay, so it kind of deflects it to the west, or to the east, sorry, from the west. Okay, here's the weird thing, guys. Winds are named for the direction they come from. All right, so our winds are westerlies because they blow from the west to the east. Okay, a wind coming out of the east is an easterly, but it blows west. Right. Okay, so that's our Coriolis effect. Right, so it's the Coriolis effect along with the convection that causes our prevailing winds. So the Coriolis effect is the deflection of any object from a straight line, okay, by the rotation of the Earth. Okay. All right, now a couple of things here, things we got to understand. One of the questions that you're going to get asked, okay, on either your final or your unit exam for this unit, or maybe both, okay, is how does the energy on Earth get transferred and moved around? Okay, and we talked about the three big things for that are convection, latent heat, and the jet stream. Okay, we got to know those three things and how they contribute. And then we got to talk about how convection and the movement of the Earth can cause patterns of prevailing winds. For some reason, people get those two things mixed up. Okay, one's talking about energy, the other's talking about air movement. All right, so we want to make sure the Coriolis effect doesn't really affect the movement of energy. Okay, it affects the movement of air. All right, so we got to make sure we keep those separate, because I often have people answer those two questions with the same answer, but they're asking different things. All right, I want you guys to answer those questions here. I'll give you a few minutes to answer them, and then we'll go through them. And then we'll pretty much be done for the day. For the first one, what's the effect of the unequal distribution of thermal energy on Earth? What does it cause? Winds, yeah. It causes convection. And winds are the evidence that convection is going on, because they are the movement of air that we feel. Okay? And that movement of air is because air is trying to move to balance the changes and differences in heat. Okay? Explain how the Coriolis effect influences the direction of winds in the northern hemisphere. Okay, well, as winds are trying to move from north to south, the Earth spins under them and deflects them to the west, making them easterly winds, okay, because they come from the east and blow to the west. If the winds are trying to move from south to north, as they do in our part of the world, okay, then they get deflected east. They get pulled along, okay, with the Earth as it tries to move that way. All right, what are the trade winds, and where do they occur? Okay, and so what latitude are they at? Near the equator. Okay, they happen near the equator. All right, there's trade winds north of the equator. There's trade winds south of the equator. Okay, for 30 degrees worth of latitude. All right, and what are jet streams? Fast winds that are very high up. Okay, we don't feel them most places on the Earth's surface because they're at least 8,000 meters or higher. All right, so we don't feel them here because we're well below them. But they do cause massive movement of air masses. Okay, that is, it brings in cold air or warm air that wouldn't have otherwise been present in a certain area, causing changes in the weather, okay, that are vital to the growth of plants, okay, in that particular area, because oftentimes they'll bring in moisture, or they'll bring in dry air that allows moisture to dry up, okay, things like that. So they bring in the changes in weather that are important for different parts of the environment. Okay, couple of little things here, okay. Remember that obviously you got an exam in a week, okay, so that you've got to be ready for, and you don't have a whole lot of time. Granted, you also don't have a lot of material to remember, so those two things go along kind of nice. Okay, we're going to do a little activity probably tomorrow. Okay, looking at specific heat capacity and latent heat on Wednesday, and then biomes on Thursday, and then review Friday. Okay, so it's going to be done right quick. Okay, so make sure you're reviewing your stuff. Okay, like I said, there'll be no more quizzes. okay, for the rest of the year. So make sure you're spending some time at night, okay, doing some studying for your final exam. Okay, start looking over chemistry maybe a little bit this week, right, so that you can start getting that straight, because it's been quite a while since we did any of that. Right, physics is probably a lot fresher in your mind than chemistry is. Right, start looking over your bio, okay, parts of the cell, what they do. Okay, look over your labs and things like that. Alrighty, questions on any of that?